All right, so today is really our last, what I might call a reinvention exercise. And when I say reinvention exercise, I mean one of these classroom activities where I ask you to create some definitions, and then we use our classroom time to kind of sort out what is the definition we want to use. There's a couple things we're going to define today, and then that's going to be the class period um, for our next class. The focus here is on multivariable functions, so that's where we're moving. We're only going to spend just a split second of time in multivariable analysis and then get even more general into something that we will call a metric space next week. But when we start multivariable analysis, I want you to think, well, what are multivariable functions? Well, normally our functions look like this. If f of x equal to y, and this is a real number, and this is also a real number. So we would say f goes from r to r. And so that's been the type of functions we've worked with all semester, where the input is a real number and the output is a real number. Well, when we're interested in multivariable functions, what we're really interested in is situations where we have f going from, say, r in to r m. And what that means is that that function has for an input all sorts of different values, x1, x2, up to xn. So we have n different input values going in, and then we have m different output values going out. So the output could be y1, y2, dot, dot, ym. So you could have as many inputs, as many outputs. Of course, these y's, each y is a function of all of these n's. So each y individually is a function of the xn's. But the actual output is the combination of all of them. So what are some examples of some of these things? Well, you're probably familiar with one of them more than the rest, and that is the example when we go from R2 to R, and that's because our input is a function in the terms of x and y, and the output is some other function that we call z. And the reason why we like this is this has a really nice visualization, and the visualization is just to let the z be a vertical axis and x and y to be some horizontal axes right here. And then what does f of xy represent? Well, it's represented, if it's nice and friendly, it's represented as a surface. As we've seen, we can have things that are not surfaces. We can have things that are not nice and friendly. So you could make up your own version of like the Dirichlet function or something in this setting and just make awful equations that do all sorts of crazy things. We're not going to invest our time too much into that because we want to just think about, well, how do the reasonable functions act in this domain? As we're thinking, we have other functions, right? So one function is the function that goes from R3 to R. And what does that look like? Well, the way I think of that one is that we have ourselves three-dimensional space, and so our inputs here are x, y, and z. And then our output is a value. So this is something where we have three-dimensional space, and then at each value in the three-dimensional space, we've assigned that an output value. So this x, y, and z is, say, given the value of something like, say, 1. And then over here, we might have that number with a value of 2. And so each point in space has a value. What might make sense would be like, so you're probably sitting in a room right now, or even if you're outdoors, you can look around and notice that each point in your room has a temperature. And where I'm sitting, there's a window on one side of the room that's bringing in a lot of sunlight, so it's really hot near there. And there's an air conditioner on the other side of the room, and so the air is really cold over there. And so the temperature is going to be different at different places in the room. And so this x, y, z function could be giving us the temperature at every point in the room. Okay, so another real common output is density. So you have some sort of object with some sort of density involved in it. Okay, finally, the last one that we'll talk about, because it's the last one that really has some sort of nice visualization, is, well, what if we wanted to go from R2 to R2? Now what that means is our inputs are all x's and y's, but then our outputs are going to be combinations of x's and y's. So it's going to be like u of xy and v of xy. One way of defining this would be to think of it maybe in some sort of parametric way. But what I think is a nice way of thinking of this is to visualize this as a vector. And if that's the case, then this would be some sort of vector field where at each point xy, so if I take that point xy, whatever equation comes out of here is assigned a vector. And so I might look, and then every point has a vector assigned to it. And so you could create a vector field. So notice that a vector field goes from R2 to R2. Okay, I'm going to get tired of drawing these in just a minute. Okay, that's probably sufficient. Okay, but what's important is notice that we can generalize this as much as we want. And so in analysis and in calculus class, the things that work for the lower ones, for those smaller dimensions, also work for the larger dimensions. You just have to think a little bit about what's, some of them actually use the fact that they're only two dimensions. In that case, you can't generalize them, but some of them are very easily generalizable. And so what you'll notice is that we can generalize ourselves to any equation where we have n inputs and m outputs. Well, today I want to ask ourselves, well, what do limits look like in this setting? And let's restrict ourselves to the idea of, say, a multivariable limit. So what would it look like to have xy approaching some number ab? Well, you can kind of guess what the picture might look like. And that is, you might have some sort of surface, and then we might have xy or ab down here. And then maybe on that surface at that ab point, we have just some empty hole. And so the question is, what would it look like to say that the limit of the sequence of that xy function equals some letter L? You might guess that you should probably use for inspiration the ideas we use with a regular limit. So what does it look like to say the limit as x goes to a of f of x equals L? And so you should use that in inspiration, but we're going to have to think a little bit harder about how to put this together. But I'm hopeful that you all can do this. So that's our first task. Our first task is complete that definition. Tell me, how do you think we should define the limit in two variables of xy approaching ab of f of x y to equal L? And then once we see that, it'll kind of make sense how we might go to further dimensions. All right. Our second task of the day focuses not on multivariable functions, but just on what is the nature of multivariable space. And to do this, let's talk a little bit about one-dimensional space, and we're going to focus on open and closed intervals. And so we know that an open interval is simply some interval like this, whereas a closed interval is some interval like this, is the interval a b, like that, with the closed brackets. And so if I were to put this on a real number line, then the a, we don't include a and we don't include b. So sometimes we might even write it like this. We might include like an open circle here at a and an open circle here at b, and then we might include everything in between. Versus for a closed interval, we have a nice closed circle here at A and a closed circle here at B. Okay, I don't think I'm shocking you with this. I think you are all familiar with what open and closed intervals are. By the way, intervals are not like doors. Doors can be either open or closed, and intervals can be neither. And what we're going to see in a moment is that we can actually create sets that are both open and closed, and we'll talk about that a little bit in class. So we can have neither. So neither is an interval, that maybe like we don't include A, but we do include B. So we have an open on one side. But what's the important thing about an interval? So if I wanted to define an interval, the way I might define an interval is we have those endpoints, but we also have everything in between. So for example, this AB might be the set of all x, such that x is between A, and B. So not only do we have the endpoints, but we also have every single point in between, and that's what makes it open. And then closed would be the exact same thing, except we would allow ourselves to equal the endpoints. Okay, so the difference here is, the important thing is that an interval isn't just the endpoints, it's every single possible point in between the endpoints. All right, but now we've got some interesting questions. What about non-intervals? What should they look like? So should they be open or closed or neither? So what if I have something that looks like this? What if I take the set of 1 over n, such that n is a natural number. This is not an interval because it has a bunch of empty spaces in here, right? So what should that interval look like? Well, that's the interval where we have, say, 1, 1/2, 1/3, 1/4, and then, they kind of go towards that limit point right there. So is this open? Is it closed? Is it neither? Okay, so that's a question we should ask ourselves. What does it mean to be open, closed, and neither in some context like that? What if we do something even stranger? Like, what if we just take the rational numbers? Should the rational numbers be open or closed or neither? Or what if we take, say, every rational number between 0 and 1? So let's do that one instead. So let's do the set of all q in q such that q is less than or equal to 0 and 1. Is that going to be open? Is that going to be closed? What is it? I'm not sure. And now what if we do something like really strange? Like what if we, I don't know, maybe this isn't super strange. What if we take something like this, the set of, and let's just take like all of the regions in between these 2 points. So what if I take the region between that point and the region in between that point and the region between that point? And so what if we go instead of writing it as a set, let's write it as a union. So what if we write a union of all the open intervals, and let's go 1 over 2n to 1 over, let's go, 2n to 1 over 2n minus 1. And we'll do this interval over every natural number. So what is this? This is taking this interval from 1 to 1/2 to 1, which would be like that, but it's an open interval. And then we'll take this interval from 1/4 to 1/3, which might look something like that. And then this interval from 1/6 to 1/5. And we're taking all those open intervals. What happens if we group all of those open intervals together? Do we get something that's open? Do we get something that's closed? Do we get something that's neither? You notice what we need here is we need a good definition of what it means to be open and closed. So that's kind of the tough question that we're confronting. All right, and then what I want us to do is, so I want us to tackle this question of what does it mean to be open and closed. And then once we tackle this question, then I want to ask ourselves, well, what, and maybe it might help us when we tackle the question of, what does it mean when we talk about these things in R2? And it turns out there's a really nice corollary of intervals in R2, and really any Rn value, and we call an open interval is similar to what we call an open ball. And if you remember, our definition of an interval was all x's between a and b, and so an open ball is going to be the set of all xy such that the distance between xy and ab and ab is less than some r. So this is an open ball of radius capital R is going to be that set. And what does that mean? Well, if I think of that in 2 dimensions, then that means I have my point AB here at the center, and I've taken my radius R, and what I've done is I've made a circle, and I made every point that falls within that circle part of my open ball. And so this is like the same idea as an interval. I purposefully did not write out a formula for distance because that's something we're going to think about and talk about, like how should we define that as we move through class the next couple days. You may write out your own formula for distance, and that would be perfect. And then similar, we have a closed ball. And the closed ball is the exact same thing with an equals, with a less than or equal sign. And so we would have that AB point in the middle, and what would we do? It would look something like this. Okay. So, but similarly, when we get to sets, we can do all sorts of really strange stuff with sets, right? So say for example, I take I take a bunch of points, just like we had. And what if I just draw, what if I just draw like 1/1, 1/2, 1/3, 1/4? What if I just draw like an open circle around each of these? What's going to happen there is if I combine all those, is that going to give me something that's open or closed? What if I draw like a closed circle, and then around that circle I put a bunch of circles, and then maybe around those circles I put a bunch of circles. Okay, so what's going to happen there? Is that going to be open or closed? So you see, we can ask all sorts of interesting, somewhat crazy questions. What if I take a set that looks like this? This will be great fun. What if I take a closed circle, and then I will not include the stuff inside this closed circle, but then I will include the stuff in that one, and not include, and will include. And so that's like, it's like this area plus this area plus this area. And then what if I keep doing that? Is that set going to be open? Is it going to be closed? How should we think about that set? And so there's all sorts of interesting types of questions here. And what you see, once again, is what we need a way of defining open and closed. Because if without those definitions, we can't hope to address these problems, because we're just working I know we're kind of working in just on our own intuition, our own feelings. We're not working with the definition. So that's going to be your second task. I want you to create your own definition. A set is open if, and I want you to say, what should we make a set to be open? And a set is closed if. And just to note, one thing that I suspect some people might say is they might want to use a word like, well, it's open if it has its boundary points attached to it, or it's open if like the end points are included in the set. Well, if you're going to use a phrase like that, you have to say what do we mean by an endpoint or a boundary point. Side note, there's actually more than one right way of defining this. One way is to think of it in terms of these boundary points. Another way, it doesn't involve those at all. And I would encourage you to kind of take your own path, and we'll talk about this in class and have a good definition of open and closed. And that definition of open and closed is going to be central to us thinking about things next week. So this is kind of looking, not only is it for tomorrow, it's also looking forward to next week. So work on